Hi there, and welcome to the lecture on earthquake waves. In this lecture, we're going to discuss what we've already talked about in the Earth's interior lecture, and then we're also going to expand on that a little bit and talk about a few more things. So let's go ahead and get started with that. Let's go to the next slide. So just as a reminder, body waves are defined as waves that travel through the entire Earth's interior. And if you recall from our lecture on the evidence for why we know what we know about the Earth's interior, the body waves were very significant in that role. That's why we've already talked about these seismic waves. If you recall, the body waves are actually compressional type of waves. So it causes the rock to expand and contract as it travels through. For most areas, that actually is very indescript, meaning if there's an earthquake and it's not a very large earthquake, the compression and expansion of the rock isn't going to be noticeable. However, for very large earthquakes, it can be, and I want to show you some examples of that here in a moment. Here's the example, cartoon example of that, where you see the waves are actually, the P wave you'll see by the purple arrows traveling from left to right, parallel to the Earth's surface, and then the dark blocks are indicating compression and expansion along that zone. And then they're even showing at the surface of the Earth how that might manifest itself. So here's some expansion of the rock, and then you see the rock opening up there, and where there might be compression, there's some buckling. Now again, that's only going to be for very large earthquakes, and that's only going to be for places near the epicenter of the quake. So we'll talk about that more in just a moment. The S waves are body waves as well, and they arrive at a seismic station later than the P wave because it travels slower than the P wave. So, but how that travels through the Earth is up and makes the solid Earth move up and down while the wave is traveling forward. So you'll see just like the P wave, the S wave travels forward as well, but makes the rock move up and down instead of expand and contract. Now let's go ahead and go to the next slide. And as we've already talked about, I'm not going to sit on this slide too long, but I just wanted to remind you where we were talking about these waves was basically trying to hone in on how we understand the different layers that we've discussed in pretty good detail in the Earth's interior module. So let's go ahead now and take a look at how these P and S waves may manifest themselves on the Earth's surface. So this is a photo that the USGS actually took after the Loma Prieta earthquake in 1989, which happened along the San Andreas Fault. And a lot of people, when they saw this photo back in '89, because it was published in a lot of different places, news media and things like that, a lot of people thought that was actually the fault zone running in this poor person's front yard. In fact, the people who live in that little red house in the photo, right after the earthquake, which of course they felt the shaking pretty good, they walked out the front door and saw the big trench in their yard and walked right back in the house. I probably would have done the same thing. And so a lot of scientists came out here because they understood that this wasn't the fault, but it's one of the only evidence of surface expression of a body wave that we have in the Bay Area. And of course this area has healed since then. It doesn't even show up anymore. But remember, this isn't the fault. This is actually away from the epicenter, nearby the epicenter, but not the fault itself. And the opening, you know, some movies make it seem like this opening goes to the center of the Earth or something like that, and that is not true at all. The depth of this opening was probably 8 or 10 feet tops. It wasn't very deep at all. And that's true of most of these openings due to expansion of the rock as the P wave travels through. Again, this is a P wave expression, not the S wave. And because the rock is opened up here, it's not buckled. That would be the expansion part of the P wave. All right, let's go ahead and go to the next slide. Now, the 1906 quake actually had a lot of surface expression. and in the form of the fault actually rupturing. I should mention in '89 when the San Andreas Fault ruptured, the rupture didn't make it all the way to the Earth's surface. So there's no photos of the rock being torn from along the fault itself. You can go to the epicenter of the Loma Prieta earthquake. In fact, there's field trip guides and such that can lead you there, but you wouldn't really see anything other than a little memorial sign saying that that was the epicenter. There wasn't any surface rupture at all along the fault or anywhere near the epicenter of the quake, actually, which, remember, can be in two different places. We talked about that in the last lecture segment. But this is from the 1906 earthquake, and this is actually in Point Reyes National Park, and was in Point Reyes National Park. The area has since healed, but the National Park Service has actually put in what is known as an earthquake trail, and there's a lot of science and literature about the San Andreas Fault running through their park. And I highly recommend you go and check that out. It's actually pretty amazing. But this isn't here anymore because over time, lots of rain, lots of erosion, weathering and erosion heals transform faults very quickly. And for that reason, we didn't even understand we had the San Andreas Fault running through our area until the 1906 earthquake. So you can imagine how surprised scientists and residents were when that quake happened, and the surface rupture was very visible. So at that point, we were able to map the San Andreas Fault, and now we know exactly where it is, and we also understand its surface expression a little bit better than we did before 1906, so that some of the more subtle features of this fault can be recognized when it couldn't be recognized before. So even though the 1906 earthquake was a tragic event, it actually provided a lot in our understanding of earthquakes in the sciences. And remember, this was all before plate tectonics. Once plate tectonics was realized, it was very easy to explain why the San Andreas Fault even existed to begin with, because of the plate motions involved with the San Andreas Fault. It was recognized in the 1960s that the San Andreas Fault was a plate boundary. In 1906, we recognized there was a fault there at all, and then in the 1960s, we recognized that it was a plate boundary at that point. So a lot of development of understanding in very recent years in the sciences for this area. All right, let's go ahead and go to the next slide and talk about surface waves now. So we just talked about body waves, which were the P and the S waves. Earthquakes, when the fault ruptures, they release the body waves and the surface waves exactly at the same time. I keep repeating that because I notice if I don't, people tend to think they're separate earthquakes altogether, that they release at different times, and this whole mishmash of misunderstanding develops. So remember, the P waves, the S waves, and these Love and Rayleigh waves, which are the surface waves, all start at the same time at the focus of an earthquake. But they travel at different speeds, and the surface waves are the slowest. So they arrive last, and they hang out longer, which means when you talk about earthquake damage, these are the waves that really cause them. A good explanation, I think I might have mentioned this in the Earth's Interior lecture, but a good way of thinking about these earthquakes, especially a moderate one, if you're in the Bay Area and you feel a moderate quake, what you'll notice is you'll feel something and you look around the room for something that's shaking. That's usually the P wave. It's kind of alerts you to they're shaking, but you're not quite sure, so you look around the room to see if something's moving. At least that's what I do. And then the S wave, which is another body wave that comes later, arrives later, is one that makes you go, okay, yep, that's an earthquake. And the surface waves make you run for cover, especially if it might be a moderate to large quake. They're the ones that go, okay, this is serious, I'm getting under something. So, and that's because they hang out the longest, and they are moving the Earth in quite a contorted sort of way. A lot of times when people report earthquakes on the news, and you're listening, one of the first things people do when they feel an earthquake is turn on the news, like either the radio or the TV. And people will call in and report what they felt. And sometimes you'll hear them say, oh, it was more of a rolling motion. All I felt was a lot of rolling. And some people say, no, 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 this was more jerky in its feeling. I don't know what that other caller was talking about it being a rolling quake. Well, it's important to realize that the love waves and the Rayleigh waves emanate differently, and so these people aren't imagining things. They're actually feeling the particular type of surface wave they're describing. The love waves, which by the way are named after a scientist with the last name of Love, basically is more of a jerky feeling, and you can see the motion indicated. You see the contorted nature of the rocks, and then you can see it's a very kind of a jerky type of motion at the surface as well. Whereas the Rayleigh waves, also named after the scientist who discovered these, are more of a rolling sensation. And both type of waves go through different areas, but what happens is the rock type the waves are traveling through will emphasize one or the other. So some people will feel the rolling sensation more than the jerking sensation, and all their mind can notice is the rolling. So that's what they report. They just say, oh, it's a rolling quake. Even though the love wave was also coming through at the same time, it just sticks out more in their head that the earthquake was more of a rolling feeling. Whereas, obviously if, somebody reports as a jerky feeling, that was the primary kind of feeling that they felt, that the Rayleigh wave was less of an impact in their area. So that's basically the difference with these surface waves. So love waves, more of the jerky sensation, Rayleigh waves, more of the rolling sensation. And let's go ahead and take a look at a seismograph now from the USGS. I think I showed you this in the Earth's Interior lecture as well. This was an earthquake. This was a Northridge quake that happened in 94, January 17th, 94. And the seismograph was in College, Alaska. And so obviously the ground displacement's in microns because you're not going to feel shaking in Alaska from Northridge quake. That's just too far away. But just because you don't feel the shaking doesn't mean that that shaking isn't present. And so here is your measurement for that. And where it was located, where the earthquake was located in Southern California, Alaska was able to record all of the wave energy that came through. And you can see the P wave arrives first because this is time passing in seconds down here. And you can see why, with the displacement, why somebody would be like, was that an earthquake? And then the S wave, you can see why that would be the confirmation. The displacement gets higher. And then the surface waves, you can really see the difference there. So that's why you can feel them better. And then that kind of dissipates after some time as well. So this is how you'll hear USGS reports about how long the earthquake lasts, and these kind of seismic records give us an idea because you can see time in seconds passing on the seismic tape. All right, so there's one more thing I want to show you before we go on to the next segment, and that is the earthquake website for the U.S. Geological Survey. This website is basically at earthquake.usgs.gov, and so it's easy to remember. But it's a very good information source for anything earthquake. So if you want to supplement what I've been talking about in the lecture with some outside reading information, aside from the textbook even, this is a really good place to go. There's a lot of articles that are published here on the right-hand side. You can see that they're scrolling between things like tsunami hazard in California, and then it'll transition into other articles to let you know where they stand. In fact, I can go ahead and push on the numbers there. You can see they need volunteers in Pleasanton, California right now. So you can read that article if you're interested. And then they talk about things they've done to the website, things like that over here. But what's really nice about this is it gives you the list of very recent earthquakes, and not just the real tiny ones. They have a list of significant earthquakes, and you can see the last one happened on the 5th, and it was a 5.3 in Hawaii. Hawaii sits in the center of the Pacific Plate, but because of its volcanic activity, rock is able to break as magma moves up, and that actually it generates into the form of an earthquake that's not related to plate movement, by the way, just related to magma movement. So you can get earthquakes other than plate boundary movement, which you probably would already realize because there's a lot more reasons rocks break besides plate tectonics, but plate tectonics is the primary reason for that breakage. So I highly recommend that you take a look at these at this website. This is a place where you can actually also report an earthquake you feel. I'll go ahead and click on this link. Did you feel it? And then you can see a map of the U.S. with different earthquakes already plotted and listed down here. And all you have to do is, if you felt an earthquake, let's say you were at the near the epicenter of the Japan earthquake in 2011, and you were out there visiting, and you felt this 5.0 that happened on the 6th of June. You can go ahead and click on that, and you can see how many people have already kind of recorded what they felt. And 3 responses in 2 cities. Yes, people in Japan will actually report to the USGS, mostly because we're kind of kindred spirits as far as earthquakes are concerned. But more importantly, there's a lot of U.S. residents over there, and they already know about the earthquakes website. And being in Japan, it's a hot spot for earthquake activity, so they like to report the earthquakes to wherever they're from. So you'll see there's some reports there. But more importantly, the location is actually showing you that this is an aftershock to that 2011 earthquake. So like I said, aftershocks can happen for quite a while after the main shock. And we'll talk more about foreshocks and aftershocks in a separate lecture on this. All right, so that is the end of this segment. I will see you in the next one. Thank you very much.